Hello everyone, welcome back to yet another session of a Nanoelectronics series of video lectures. Well, this is our fifth session, and in our previous four sessions, we have discussed the transport of nanostructures. It was under the effect of an electric field that we discussed so far. We had the parallel transport, perpendicular transport, we discussed about hot electrons, the quantum transport in nanostructures, and even the Coulomb blockade. So from now on, we are going to see the effect that magnetic field has on nanostructures. So this session deals with the behavior of crystals under the effect of a magnetic field. Well, when I say crystal, I am talking about three-dimensional nanostructures. So crystals are basically three-dimensional nanostructures. Now, as we apply high magnetic field to a crystal or say to any three-dimensional nanostructures, various effects happen to that crystal. The crystal may collapse its energy states of the conduction electrons into Landau levels. Initially, the crystals have stable energy states. Due to the effect of a magnetic field, these energy states will collapse into Landau levels. Now, what is this Landau levels? Landau levels are nothing but discrete energy levels which any charged particle can occupy. So, suppose you have a energy level say E. Initially say let's suppose that the crystal had an energy level of E. On the effect of a magnetic field, this energy level collapses into intermediate energy levels, or I would say subbands. So these discrete energy levels from E to E1, E2, E3, E4, these discrete energy levels are called Landau levels. So in this session, whenever I say Landau levels, I am referring to the discrete energy levels that any charged particle can occupy. In fact, charged particle can occupy only those discrete energy levels. Those energy levels are called Landau levels, right? So apart from this collapse of the energy state, some other effects may also occur. That is the collision or oscillation in the magnetization when your magnetic flux varies. As your magnetic field varies, the magnetic flux varies, and this may result in oscillations. So apart from the collapse, you may also get oscillation in the magnetization. We may also get oscillation of electrical resistivity as a function of magnetic field. So the oscillation may be in terms of the electrical resistivity, or it may also be in terms of the magnetization. So we have two types of oscillation, and another possibility is the collapse of the energy states. So whenever a crystal faces a magnetic field, any of these three effects may happen, and we shall see all these three effects in detail. Now, these effects are basically due to the quantization of energy of conduction electrons. That's what we mentioned about Landau levels. So what happens is the energy level of the conduction electrons get quantized into sub-energy levels, En. When n equal to 1, you have your energy level E1, n equal to 2, you have E2. So E1, E2, E3, E4, these are your sub-bands of energy. So what happens, the conduction electrons get quantized into energy levels given by this equation. So I hope all the terms are familiar. Yeah. There is no new term used here, right? Well, let's familiarize with omega c. So when we talk about omega, it's definitely the frequency. So omega c is a cyclotron frequency, or the frequency of your oscillation. So basically these oscillations are simple harmonic oscillations, and its frequency is represented by omega c, the cyclotron frequency. So here N is your energy level, H bar is the constant which we replace, H by 2 pi is replaced by H bar. Omega c, the cyclotron frequency, again H bar. Kz is your wave vector in the z direction. See, here I have specified Kz because I have considered my magnetic field Bz in the z direction. So your wave vector is in the z direction. Me is your effective mass of the electron. So I hope these terms are clear. So apart from this, what happens is the magnetic field, I have applied the magnetic field B in the z direction. Now if my electrons are moving along the z direction, the magnetic field will not alter such electrons or the motion of such electrons. So the magnetic field in a particular direction, for here it is in the z direction, will not affect or will not exert a force on those electrons which is moving parallel to it. As a result, the electrons in the z direction behave as if they are free electrons. Since the magnetic field is along the z direction, the electrons moving along z direction will not get affected. But the electrons in the xy direction will have change in their properties. It may be any of the three effects that we mentioned earlier: oscillations or collapse. Now, what happens is, when our magnetic field is applied, the 3D allowed state in our K space will collapse into concentric tubes parallel to our magnetic field B bar with a degeneracy of Gn equal to E B divided by pi into H. So, Gn is your degeneracy factor. This is nothing but, see, we have told that on the action of a magnetic field, an electron which was initially occupying an energy state E collapses or it becomes degenerate. Degenerate means, well, their properties are now more unique. Initially it was just an energy level E. Now they will have, since they collapse, they will have multiple energy levels or sub bands like E1, E2, E3 and so on. So when this magnetic field acts, the allowed state in the K space collapses into concentric tubes parallel to our magnetic field, and their degeneracy factor is given by this equation. Right? Is that clear? Okay. Now how can I represent it? I'm sorry. So we have the wave vector Kz and the energy. A plot of this shows that we have concentric wave vectors for the different Landau levels, n equal to 0, n equal to 1, 2, 3. All these are concentric in nature. Similarly, the DOS function of a 3D structure. So, if we are not giving any kind of magnetic field, we are familiar that for a 3-dimensional for a 3-dimensional nanostructure, the DOS function follows this curve, this dotted line. But on the action of your magnetic field, the density of state changes due to the collapse of your energy bands. So this is the effect the magnetic field has on a crystal. So what we discussed was what are the effects that this magnetic field has on a crystal. It may be the collapse or it may be oscillations. So how can we mathematically represent this collapse? So we had the equation for different energy levels, or we introduced the Landau levels, the concept of Landau levels. So what was the equation for the energy level or subbands or even the lantern levels, whatever be the name you call it, right? Now later we saw what is the effect that the magnetic field has on electrons. If the electron motion and the direction of a field is in the same direction, the magnetic field doesn't affect those electrons, right? And we saw that in the other two direction, if the magnetic field is in z direction, in x and y direction the electron motion is affected or they become degenerate, or else there is a oscillation for those electrons. So that's what we looked into so far. Now let's see what is the effect that the magnetic field has on a low dimensional system, which means we will be considering two dimensional system, because we just discussed the effect on a crystal which was a three dimensional. So let's see what is the effect that the magnetic field has on a lower dimension system or a two dimensional system. For two dimensional electron systems, the magnetic field will completely quantize their energy spectrum. Why? There is just two dimensions. So suppose your structure is in x and y direction, your field magnetic field is applied in z direction, which means the electrons in the x and y will be quantized, their energy levels will be quantized. As a result, the magnetic field will completely quantize the energy levels of a 2D electron system. So let's try to determine an equation for that. So we'll start with the Schrödinger wave equation. Here what we consider is that we are considering a magnetic field in the z direction. Now our vector potential A bar, vector potential A bar actually has its components in x and y direction because it represents your electron. But we assume that A bar has only one component, or A bar, the vector A bar is not dependent on its y coordinate. In such a case, I can represent AY equal to BX, that is y coordinate depends on x terms. B is your magnetic field, right? So that is the one condition that I take for my when I am applying this to my Schrödinger equation. One, the vector potential has only one component, and the momentum, normally we represent the momentum by P, but in this case when we consider the effect of magnetic field in low dimension, let me replace the momentum by P minus QA. P is your momentum, Q your charge, and A your vector potential. Using this, I am rewriting my Schrödinger wave equation as this. Same equation, I have just substituted the momentum by this new part and even the wave vector. That's it. Now let's start simplifying this. What I have done is I have expanded this bracket. This of the form a plus b the whole square. So I can write this as a square plus 2ab plus b square. So a square will give you I square h square dou square by dou y square. I square is minus. So it is minus h, opening the bracket, minus h by 2m dou square by dou y square. Let me combine these terms because even here it is minus h square by 2m. So I have this term minus h square by 2m dou square by dou x square and this expansion, right. Now the second expansion is, what is it? 2ab, right? 2I h e b x dou by dou y divided by 2m, giving you, cancelling the 2 in the numerator and denominator, you get this term. And finally e bx whole square divided by 2m. The rest I am just rewriting it. So what I have done is I have applied the previous assumptions in my Schrödinger wave equation. I have expanded this bracket and combined the common terms. Here we had common terms, I just combined it. Now the solution for this equation, solution means we have to find this wave function is of the form psi xy equal to psi of x into e raised to I ky. Now let me use this into this equation and make this equation only dependent on x, from which I obtain this equation. So I have used this equation into this previous equation, and here I have also considered that your vector potential A bar has only y components, has only x components, it does not depend on y, due to which I have rearranged this. I have eliminated all the y terms, obtaining this equation. Here there is a term x naught, which is nothing but my constant hk by eb. So wherever this term hk by eb has come, I just replace this by a constant x naught, similar to what we have done during the Schrodinger wave equation derivation, right. In this case, the equation for energy level of the substates or subbands for a 2D system is given by En equal to n plus 1 by 2 h bar omega c. So what we have done is, we just applied our condition, vector potential momentum condition, in our Schrodinger wave equation, expanded this, simplified, obtained a solution. Now we considered that our function A bar is dependent only on x term, not on y. Eliminated the y terms and substituted hk by eb by a constant x naught. That's it. And finally, the energy for your eigenstates or your subbands for the two-dimensional system is given by this equation. Just have to study that. Thus, we can see that the energy of the electrons due to the effect of magnetic field depends on n and the frequency omega c. Now let's see what is the effect this magnetic field has on the density of state function of a 2D system. So we have seen what is their effect on a crystal, on a 3-dimensional system, on a 2-dimensional system. Now let's see what is their effect on the DOS of a 2-dimensional system. So if you are applying a strong magnetic field for a 2-dimensional electron system, the electron system follows a cyclotronic orbital action, which means, or it's a simple harmonic orbital behavior. Now initially, if there was if there was no magnetic field for a 2-dimensional system, their DOS was a straight line, right? It was just a straight line. However, with the effect of a magnetic field, we could see that these levels just got broadened, or and there was a delta function at each Landau level. So this was your ideal condition, this straight line. Due to this effect of your magnetic field, there was a broadening in these peaks. Why was that so? This is because your electrons have suffered scattering, and as a result the delta function just got broadened. This broadening effect at each level, each energy level, was caused by the impurities or other defects, or whatever be it, or the lattice vibration, whatever impurities or whatever scattering is possible in that structure, it is due to that. And this widening is characterized by your energy width tau. So the broadening from the ideal condition was basically due to the scattering by impurities or by defects in the system, or even due to the lattice vibration. And this broadening effect is determined by the energy width tau. If you want to observe Landau levels, or if you want to specifically identify these Landau levels, we must need the electron mobility to be very high. Only then can we determine their intermediate energy levels or their Landau levels. Now, since all the levels in the interval, since they are multiples of h omega c, they collapse to the same Landau level, the degeneracy of the Landau level is given by this equation. You don't have to study the derivation of such equations, just have to note it, right? So that's what we have seen in this section. In this session, what is the effect that the magnetic field has on a crystal? So in the case of crystal, it may be a collapse or oscillation. Oscillation may be considering the electrical resistivity or the magnetization. And there we saw how the magnetic field in z direction affect electrons in x, y and z directions. No change in z direction, but in x and y the electrons face some kind of oscillations. Now coming to two-dimensional system, the two-dimensional electron systems, their magnetic field or their energy is completely quantized by this magnetic field. We saw a very small derivation, not derivation, some kind of an analysis, and from that we obtained the energy for the eigenstate or for the Landau levels. And there in two-dimensional system, the energy of the eigenstate was dependent only on the quantum number n as well as the frequency omega c. And finally we saw what was the effect that magnetic field has on the DOS function. There was a broadening for a two-dimensional system. Ideally it should be a straight line, but due to the effect of a magnetic field there was a broadening. The delta function just got broadened due to the scattering by the defects. So we just noted the equation for the degeneracy also. Please go through it. I hope this session is clear. Thank you.